Living and working in microgravity. It isn't easy to provide for eating, drinking, and sleeping, cleaning, and personal hygiene on the space station. Air, water, materials, and human body act differently in space because of microgravity. Equipment we use on Earth would not work the same way, or not work at all aboard the space station. Food for the International Space Station crew is nutritious and compact, and tasty most of the time. The food must come in convenient packages for easy handling and weightlessness. Astronauts select their menu before going to space station, but their choices are limited. Fresh foods sometimes arrive with new crew members, although they do not last long. Water must be added to most items to make them edible. Personal hygiene is a novel experience on the International Space Station. A crew member takes a shower using a hand sprayer and washcloth. Because loose water droplets floating around in weightlessness can be a hazard for electrical equipment, the bather must catch the sprayed water in a sponge or washcloth, then use the wet cloth to clean themselves. In space, toothpaste is swallowed. A special dry shampoo is rubbed into the hair with a towel without needing to be rinsed. When shaving or cutting hair, a vacuum tube is used to collect the hair and keeping it out of the equipment and air filters. Every few months, Russia launches a Progress resupply rocket stocked with food, water, personal items, and spare parts. The Progress spacecraft attaches a Russian-made module. The crew uses supplies from Progress and fills the craft with trash. Eventually, the Progress undocks from the station and burns up in the atmosphere, incinerating the trash it carries. Robot spacecraft from the European Space Agency, Japan, and the United States can also be launched by expendable rockets to resupply ISIS. Japan's H-2 transfer vehicle, HTV, and SpaceX Dragon cargo ship are reusable crafts that can return scientific samples to Earth. The ISS, the International Space Station, is designed to be maintained while in orbit. Most parts, inside or outside, can be disconnected, replaced, and reconnected, like a light bulb. This makes it easier for the crew to make repairs. Crew members can work outside for about 8 hours at a time, wearing spacesuits, of course. While they work in space, they have several ways to move around. They can pull themselves hand over hand, using handholds on the modules. They can ride on a small rail cart along the truss of the station, or they can hitch a ride on a robot arm. Crew members use tether lines to stay attached to the International Space Station, keeping them from drifting away if they lose their grip. Crew member wear small gas jetpacks that can get them back to the station if they get separated from the spacecraft. Astronauts wear spacesuits made of 14 layers of fabric. Going from inside out, there's nylon tricot, spandex, a lacing of plastic tubes, urethane-coated nylon, polyester fiber, ripstop nylon, 7 layers of polyester film, an outer layer made with fibers that are lighter and tougher than steel. Those same stronger than steel fibers, called aramid fibers, are used to make bulletproof vests for police officers and flame-proof suits for firefighters. One of the best known aramids has the trade name Kevlar. The International Space Station can hold a crew of 3 to 6 people, a group called an expedition. For up to 6 months, crew members arrive and depart in either a space shuttle or Soyuz spacecraft. Most occupants have been American astronauts or Russian cosmonauts, but European and Japanese astronauts have also been part of crews. A few wealthy tourists have paid to visit for a few days to do experiments or educational outreach or just relax, but are not considered an official part of the crew. Official language is English, but a lot of Russian gets spoken too. The first crew, known as Expedition 1, boarded the station in November 2000. American commander Bill Shepard and Russians Yuri Gidzenko and Sergei Krikalev stayed for 4 months. They were replaced by Expedition 2, which had a Russian commander and 2 Americans, including the first woman on the station, Susan Helms. Most crews have a commander, a flight engineer, and a science officer. The commander has the overall responsibility for running the station and managing the crew. The engineer's main duty is to keep the station's mechanical and electrical systems working properly. The science officer supervises scientific and medical experiments. Additional crew members will work mainly on the science experiments. All the crew take part in medical experiments and station maintenance. The International Space Station is about the length and width of a football field, including the end zones, and has an internal pressurized volume similar in size as a passenger cabin of a 747 jet. Science on the International Space Station. The International Space Station may have as many as 6 laboratory modules, becoming 5 times larger and having more research abilities than any previous space station. The United States provided Destiny Laboratory. Japan provided Kibo module, and the European Space Agency provided Columbus module. Russia may provide up to 3 research modules. Some experiments done aboard the ISS study effects of microgravity on the human body and research how plants and animals could behave at different levels of gravity, such as 1/6 the Earth's gravity as on the Moon, or 1/3 as on Mars. Other experiments investigate various properties of physics and chemistry, while still others may produce new materials that cannot be made on Earth. Medical research aboard the International Space Station may lead to the development of drugs that can stop bone loss. Besides helping space travelers, such drugs would benefit millions of older people. Other studies in space might lead to treatment for cancer or find ways to make purer forms of medicines. Researchers are also working to develop vaccines for Salmonella and Staphylococcus aureus, which causes antibiotic-resistant staph infections of Staphylococcus aureus. Scientists want to better understand how physical laws and chemical processes work in space. Materials act differently, fluids flow differently, and fire burns differently in a microgravity environment. New materials could be made in orbit from substances that will not stay mixed on Earth due to their different densities. Studies of the process of burning could lead to improvements in firefighting techniques and equipment, or help strengthen pollution controls. Flames in microgravity look different from the way we see. On Earth, flame is shaped like a teardrop and yellow in color. On the International Space Station, it would be round and blue. All mixed up. Imagine you are trying to mix molten lead and molten aluminum. A large difference in density would cause them to separate in Earth's gravity before the metals could cool into a solid metal. In weightlessness, however, the two could mix to form a new material, an alloy. Perhaps a new material that was similarly made could be used to build future spacecraft. The knowledge gained from experiments that are not possible on Earth will benefit us all. The International Space Station is the next step to satisfy humanity's ancient yearning to explore, learn, and achieve. From this outpost, we can continue to explore the frontier of space, the new era of space transportation. With the retirement of the Space Shuttle in 2011, the only regular crew transport to the International Space Station via the Russian Soyuz crew vehicle. In the United States, a number of companies are working hard to provide the next generation of cargo and crew vehicles. Having multiple launch vehicles available reduces the risk to the space station crew. The military was concerned about not having their ability to put satellites in orbit after cargo was restricted following the Challenger accident. In the mid-1990s, it decided to work with Boeing and Lockheed Martin to develop a pair of launch vehicles, Delta IV and Atlas V, respectively, that could lift large assets into space. In late 2020, Beale Aerospace tried to build inexpensive vehicles to launch commercial satellites to geostationary orbit, and at one point fired the largest liquid rocket motor developed in the United States since Apollo. Government subsidies to commercial competitors above the company to close to 2001. Shortly thereafter, SpaceX began developing the Merlin rocket motor and Falcon family of launch vehicles, which with the larger Falcon 9 rocket having its first successful delivery payload to orbit in 2010. The delivery of crew is more complicated. NASA began working with industry in 2004 to provide alternatives to the shuttle program. Many proposals recommended use of existing Alpha and Delta rockets. NASA later decided to develop its own launch vehicle that used elements of the space shuttle. This became the Ares rocket component of the Constellation program to go to Mars by way of the Moon. Funding was cut in 2010, which left private efforts already underway as the only potential near-term solution. Originally an element of canceled Constellation program, the Orion multi-purpose crew vehicle is designed for crewed missions beyond low Earth orbit. SpaceX designed its rocket to launch the company's Dragon capsule, which will also have a crew version. One design feature of the Dragon capsule is that instead of using tractor motors on the nose of the capsule, as with Apollo and Orion, that drag the capsule away from an emergency situation, the Dragon instead uses pusher motors in the base to push the capsule away from the blossoming crisis. SpaceX launched Dragon in October 2012 on its first commercial resupply mission to the International Space Station. Boeing and Bigelow Aerospace have teamed up to develop and provide the CST-1000 capsule, designed to be launched on Delta Atlas Falcon rockets for launching astronauts into low Earth orbit. The International Space Station will be the primary destination for global space activities. As more transport solutions are developed, especially for the crew, there will be increasing pressure for spacecraft and other orbital inclinations to transport to those facilities.